Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the Sky and Telescope series. And I am very happy to have author Ted Rafferty with us today. Hey, Ted.
Hello. How are you doing?
I'm doing good on this February 24th of 2022 as we shoot this. And I have to say that I'm really looking forward to equinox coming. In Phoenix. So equinox will actually be here a little before in about a month. Ted, where are you located at?
I'm in Gaithersburg, Maryland, which is just to the north of Washington, D.C.
Snow on the ground?
No, not today. It was 70 degrees yesterday, so no snow.
Wow, you were warmer than Phoenix yesterday. That's pretty amazing. Well, good. So hopefully you won't get any more nor'easters rolling down. So
never know.
Never know. You got some pretty cool pictures on your wall there. Is that a relationship, or it almost looks like Mark Twain almost?
That is Hal Holbrook playing Mark Twain.
Yeah. Okay. Very good. Yep. Very cool. Very nice. And Ted, what do you like to do in astronomy?
Well, I was a professional astronomer for 32 years. Well, I was an amateur even before that. Working at the Naval Observatory. Mainly working in positional astronomy, doing instrumentation or in data analysis. I retired 16 years ago. I have a couple telescopes that I set up in my backyard, and I'm quite into imaging with a CCD camera.
Very cool. Very cool. What kind of scope do you got?
The bigger one is a 10-inch Orion f4.7.
Okay.
And then I have an old S-Big imager. And then I've got also a refractor, and then I've also modified a 200 millimeter lens to adapt to the CCD.
Very
so
cool.
I have 3 different focal lengths.
Do you just go out in your backyard, or do you go out somewhere?
My plan was to go remote, but I thought I'd learn the equipment first by imaging from my backyard. And I was so impressed with what I was able to get, especially using narrowband filters. And being able to have the house just 30 feet away from the telescope while the telescope is guiding for 2 hours, it's quite nice to be able to sit inside and do something else.
Absolutely. Absolutely. So you're going to be putting a dome in your backyard?
No, the 10 inches just light enough for me to carry the parts out. So I carry the parts out before the beginning of the night. And then when I stop observing, I pull the optics in the laptop computer, and then I get the mount in the next day.
Very cool. Very cool.
And that seems to be, at least I don't have the problem and the cost of building a dome. And it seems to work out very well. Again, it's one of these things where you experiment, and is what you have good enough? I'm not looking for perfection. I'm looking for good enough.
Yeah. Yeah, very cool. And speaking of approximations and perfections, this is going to take us to this very lovely March 2022 article, Sky and Telescope, on Mason and Dixon's Great Venus Adventure. And Ted, take us away.
Well, I've heard of Mason and Dixon because, of course, the Mason-Dixon line is right along the Maryland and Pennsylvania border. And when I was researching other fields of interest, I researched an article on James Cook that I did for Sky and Telescope a number of years ago.
Okay.
I kept seeing Mason's name and even Dixon's name pop up. So I knew that most everybody knew the story about the Mason-Dixon line, but I'm not sure that they knew that they had actually teamed up earlier to do this transit of Venus in 1761.
Yeah. Yeah, I didn't yet. In fact, it was news to me that they were astronomers.
Yes. Well, Mason must have been a full-blown astronomer who worked at Greenwich. Mostly brought in to work on lunar tables. But Dixon appears to be just an amateur astronomer, though he had some surveying background.
Right.
And because he had connections at Greenwich Observatory, he had some friends there, he was able to get selected to go with Mason to observe the observe the transit.
Cool.
So,
Cool. And we got suitably, well, we got some musical scales here. And yeah, we got a line of transit, Venus's path. Very cool. Nice artwork on this, by the way.
yeah, that's thanks to Sky Telescope, of course.
Yay, very nice work. Okay.
So the main purpose of the transit of Venus was to try to determine the distance between the Earth and the Sun.
Okay.
In the late 1600s, Kepler determined his third law that was based on observations that he was able to get from other people on of the different planets. And he was able to derive this, the ratio of the sizes of the orbits. But because the observations were made from the Earth, there was no scale.
Right.
So they did not know how many kilometers or how many miles it were to the planets. They only knew that Mercury was some fraction of the distance further than the Earth and things like that.
Right.
So the idea was if you could determine the distance between the Earth and any other solar system object,
And you set the scale.
that orbit around the sun, then they could determine the distance. And
Cool.
so they tried to do it with Mars first, with the background stars, and that didn't work because Mars was too far away from the Earth. They tried it with the Mercury transits of Mercury, but there not only was Mercury too far from the Earth, but it was also too close to the sun. So you could not see enough of the shift.
Okay.
So Edmund Hale in 1677 suggested that they used the transit of Venus of 1761.
Okay.
And his suggestion was to time the transit from start to finish from two widely separated locations, preferably to the north and to the south.
Okay.
If by doing that, you did not have to know the exact longitude. You only needed to know how long it took Venus to cross the sun.
Right.
And then by the lengths of those paths, you could determine how far away the two paths were on the sun. And then if you knew the distance from the two locations on the Earth, you then could figure out the distance to the sun or to Venus.
Venus. Very cool. Very cool. Strict geometry method there. Okay.
Yeah, it's
geometrical.
I tried to figure it out, and I had a little bit of a problem trying to figure out why longitude wasn't important, but I think I sort of see what it was. But again, the main point was that you had to time the entire transit. It couldn't be part of the transit, it had to be the entire transit. Once you started only measuring part, if you timed the first, second, third, or fourth contacts, if you only did one or two of them, you had to know your longitude.
Right. Yeah. Okay.
So, and that back in 1761 was not an easy thing to do.
Challenge.
I mean, the Greenwich Observatory was established for learning how to determine longitude from a ship. That was one of the key things that they were interested in, besides the distance to the sun for Kepler's laws. So the other two methods was to time the contacts, but then you would also need the longitude, and you had to know your local time, and of course you had to know your latitude, because you need the latitude so you can determine the distance between the two locations.
Right.
And the other one was to measure the path of Venus across the face of the sun, and then measure the difference in the paths of the two, from the two places.
Oh, yeah.
So you got to remember that what Mason and Dixon were doing was only half of the experiment. Okay. They had to have somebody else at another location doing the similar thing.
Okay.
And of course, they never knew if anybody was able to do it or not. So they just had to make sure that they got all the information they needed, so their part of the observations would be complete, and then hopefully somebody else did the same thing in the northern hemisphere.
Hopefully.
So the idea the British wanted to do was that they had a number of people already stationed in Europe and England, so they needed people in the southern hemisphere. So they sent one team with Neville Maskelyne down to St. Helena in the Atlantic Ocean.
Okay.
And they wanted to send Mason and Dixon to Samoa in, near the Indonesia.
Right.
And they figured that, between all of those, eventually they would have enough information or enough observations that they could determine the parallax. Unfortunately, there was a delay in the ship for carrying Mason and Dixon, and they weren't able to leave until early January. And unfortunately, the war was going on at the time with the French, and they got attacked by a French frigate, and a number of crewmen were killed. A number of supplies had to be thrown overboard to make it so they could use their guns. And of course, they had to turn around and go back and get repairs. So by the time they did leave England on February 3rd of 1761, they knew it was probably going to be impossible for them to make it to Samoa. So 2.5 months later, when they got to Cape Town, they decided that, and with the captain, they decided that that was good enough. So they stopped there and set up their equipment. So the equipment they had to have a clock, and it was a pendulum clock, so it wasn't a clock that they could keep running from England. They had to set it up and then start the clock and then determine the time. Okay. They needed an instrument to determine the transit of stars, which was the Astronomical Quadrant, which they also could use to determine their latitude, because the quadrant has a large section of circle, and there's a plumb bob that hangs down, and they can measure and use that as the reference for where the nadir was to determine the zenith distance for the stars, and then by knowing the declinations of the stars, they could then determine their latitude. The other instruments were the two Gregorian reflectors, which in my article, I made a mistake in that they were referred to as 2-foot Gregorian reflectors. And I thought that the 2-foot referred to their focal length. Oh. And it doesn't. It refers to the focal length of the mirror, and not the effective focal length of the telescope. And so the effective focal length of the telescope is closer to 3 feet than it is to 2.
Got it. Wow.
So they had those telescopes. They had 2 of them, and they also had a Dolan split objective micrometer. Okay. And if you have that one illustration that I sent that shows that.
Let's take a look at some extra bonus material associated with this article. And so I'm going to do a little screen share of some bonus images. And there we go.
Yeah. All right. So this thing fitted on the front of the telescope. So, and it had 2 pieces of optics that you could turn a flexible rod from the back end of the telescope that would separate the 2 pieces, as one would go one way, the other one would go another way. And there was a scale, which is labeled Y, and they could measure how far those 2 optics separated from one another.
Got it. Okay.
But he also had the rotate micrometer, because what he wanted to measure was the limb, the sun's furthest limb from Venus, and Venus's furthest limb from the furthest limb of the sun. I don't know if that makes sense.
I got it.
Everyone go to that the next illustration.
Okay, this one?
No, it's the other one.
This one.
That's it.
There you go.
So on the left-hand side, the top view shows when the two pieces, the two halves of the micrometer are aligned to one another, you see the images the way they really are.
Okay.
And then when you separate them, you can bring the image of Venus to touch the limb of the sun. So, and then in the case on the left, maybe I got it backwards on left and right.
It's parity.
And but as Venus moves across the sun, Mason would have to rotate the micrometer, which it shows on the one side where he has to rotate it.
Right.
So, the telescope's it's not on an equatorial mount, so he's got to move the telescope to track the motion of the rotation, the apparent rotation of the apparent rotation of the apparent motion of the sun caused by the Earth's rotation. And then he had to adjust the spacing separation of the two optics and adjust the rotation with his two. So his two hands were occupied while looking through the eyepiece.
Very cool.
Could not have been easy.
Yeah, no.
And I imagine that what happened was that when he made a measurement, he would have told Dixon to note the time, and then Dixon would walk in front of the telescope and then read off on the scale what the separation of the two halves were.
There you go.
So Mason could stay at the eyepiece end of the telescope.
Right. Right.
And it took me a while to try to figure out why Mason measured these things the way he did. And the next illustration shows that if you take S1 as being the furthest limb from Venus and VL1 being the furthest limb from that limb, you'll notice that the line between them goes through both the center of the sun and the center of Venus.
Yes.
And Mason also measured the diameter of the sun, and he also measured the diameter of Venus. So it's like, subtracting the radius of the sun and the radius from Venus from the measurement, you get the distance between the center of the sun to the center of Venus, which actually I thought was pretty clever.
That's pretty neat. Very nifty.
So he made 15 measurements of Venus on the surface of in the path of the sun with that micrometer.
Okay.
And then before the Venus was to leave the disk of the sun, he had to remove the micrometer so he could time the third and fourth contact of the limbs. And because they had two telescopes, both Mason and Dixon could time it.
Good.
But because the only way they could tell what time it was is they used a method called the eye and ear method, where they would look at the clock, see what time it was, memorize that, and then count off the seconds. So as they were looking through the telescope, they would have to remember what the time was and then jot it down.
Wow.
That also must have been an awkward thing.
That's why they had assistants, I think, to help with some of this stuff. But yeah.
Right, but as far as I can tell, it was just the two of them.
Wow.
And when they timed both the third and fourth contact, both of them did it, but neither of them agreed. Dixon's was always early. He was 4 seconds early for the third contact, 2 seconds early for the fourth contact, which is just an indication of just how difficult it is to tell that it actually crossed the limb of the sun. So.
Yeah. Let's go back to the article here.
So the month preceding the transit, they spent all their time determining the rate of their clock. The clocks do not keep perfect time. They have a slight, they're either running slightly too fast or slightly too slow. They could have adjusted the pendulum to account for that, but instead they just let the clock exactly the way it was, figured out that, you know, every hour it was 2 seconds fast, and then they would adjust their time accordingly to the rate.
Yes.
So they spent that first month determining the rate of the clock and the latitude of their station. And then after the transit, they remained in Cape Town for almost 2.5 months. And during that time, they also continued to determine the rate of the clock, or test the rate of the clock,
right,
make more observations for their latitude, but then also making timing the eclipses of the satellites of Jupiter, which is how they determine their longitude. So the idea was that
yeah,
they understood the motions of the satellites of Jupiter well enough that they could say that when Io transited on a particular, or went behind Jupiter on a particular night, that in England it would happen at such and such a time. And then if you timed it at your local time where you were, you then could determine the difference and then determine their longitude.
yes, okay, got it, very cool.
So so Mason and Dixon observed, well, at least one of them observed the transit 17 times. Twice, both of them did it. Again, there was a difference between what Mason's thought the eclipse was and when Dixon was.
Fair enough.
But one thing I have to give them credit for is that when they presented their data, when they got back, they gave them everything,
Right,
including that the times didn't agree. There were in their notes, Mason would actually indicate which measurements he thought were dubious. So he was trying to be as honest as he possibly can, because of course he couldn't tell if his times were correct or Dixon's were.
right.
So when they got back to England, they found out that there were quite a few measurements made in the Northern Hemisphere.
Yay.
But people weren't quite as good as Mason and Dixon were in determining their longitude or the rate of the clock. And a lot of the people were amateur astronomers, and so their measurements weren't very useful. And they did compare the timings of the third and fourth contact, but the scatter was so great that they never could get a good handle on the parallax.
Okay, drats.
But what it turns out that when the next transit of Venus in 1769, they tried it. The British and a number of other countries tried to do it again, even more from more different locations.
Right.
And those results also did not come up with good results. And then in the 1874 and 1882 transits, where they had much better equipment, even those results just didn't work. Venus was just too far from the sun to get a good parallax from. So they had to wait until the 1900s until the minor planet Eros made a number of close passes to the Earth, and there they could determine the parallax well enough to determine the distance between the Earth and the Sun. But now that's all being done with radar and with timing signals from satellites.
Right. Atomic clocks a little bit.
Yes.
The precision that we get.
So the biggest thing that Mason-Dixon got out of it, of course, was the contract to do the Mason and Dixon line. And it's what they're most known for, though at the time, they apparently weren't known for it at all, because as I noted in the article, when Mason decided to leave England and come to the United States, soon after he arrived, he died in Philadelphia, and he was buried in an unmarked grave. So they're not sure which grave was his. And Dixon, I don't know much about that, but I think that the term Mason-Dixon line was not something that was well used during their lifetime.
Right. That came later. Very cool. Very nice. Yeah. I think it's a nice point here in the ending paragraph, right? And so you go through all this effort, and the results didn't quite stack up the way one might have hoped. And this is actually somewhat common, I would say. You don't quite get the accuracy or the precision that one would have liked, but you got out there and did it.
Right.
And it's a help. It will help the next set of measurements come along that will improve upon those, because now they know what the errors in let's say longitude were, or the timing is, or whatever it might be. So,
well, they used quite a bit of that in the 1874 and 1882 transits. The American expeditions, they took there were 8 of them, and they took identical pieces of equipment, much better telescopes, much better clocks, a small transit instrument, and most importantly, photoheliostats with a focal length of 40 feet.
Ooh.
So to photograph the Venus crossing the limb.
Right.
And even with all that, they still could not come up with good results.
Good.
It was one of these things. It was a great idea on paper, but it just didn't work in real life.
Gee, let me count how many times that's happened to me. Okay, very good. Very cool. Very cool. Ted, thank you so much for walking us through your very lovely article.
Enjoyed it.
Yeah. And so where do we kind of go from here? Now that this article is published, is there an effort to locate unmarked graves? Do we actually still have all of the instruments that they used during that transit, or some of them lost? Or yeah.
Well, most of those instruments are in England, okay. And I think the clocks are too. I'm not sure that they know exactly which clocks they were. There's some confusion, since some of the equipment also was used for the 1769 transit. Even that James Cook took with them. They're not absolutely sure which clock he took or which telescope he took. So the record keeping wasn't the best for that.
Okay.
My interest in Mason-Dixon, for the most part, probably ends with that article.
Okay.
My main interest, since my background was in instrumentation, was to focus on the instrumentation that they used, and especially the micrometer, which I thought was very interesting.
Nifty at the time, yes.
So I probably will try to do some other articles. My other articles for Sky Telescope have all been connected with instrumentation.
Very nice. Cool. Well, I look forward to taking a look at one of your future articles when you talk about some of that 1800s or earlier, 1700s instrumentation. Very nice.
Well, the one thing that's been very nice about all of these things is that I find writing the articles to be the worst part of the whole thing, besides finding good illustrations. Good illustrations are hard to find too.
Indeed.
But the research was fascinating, because it would take you all over the place. And as I said, in researching for my Cook article, when I saw Mason's name pop up and Dixon's name popped up, that connection I thought was interesting. So
I didn't know.
I almost enjoy the research more than I do the writing.
Oh, let me count the number of people who I know do that. That's because the research is fun and writing is a pain.
Yeah.
Indeed. Very cool. Ted, I want to thank you so much for walking us through your March 2022 Sky and Telescope, and that will do. And I hope this made your astronomy day just a little bit better, everyone, and we will see you on the next one. Bye-bye.